Hello and welcome back dear student in the next lecture of the topic solution. So all of you welcome in the next lecture of the topic solution. So we have started with our second topic solution, and in that in the last lecture we have done colligative property, or we have started the colligative property, and as we know there are four colligative properties. Colligative properties are the properties of a solution which depends on the number of solute particles and not on the nature of solute particles. And therefore there are four colligative properties as vapor pressure lowering, elevation in boiling point, depression in freezing point, and the osmotic pressure. So in the last lecture we have done our first colligative property, that is lowering of vapor pressure. Lowering of vapor pressure, that means there is a lowering of vapor pressure of a solution takes place when we add a non-volatile, non-electrolyte solute to the solvent. Then it forms a solution. So the relative lowering of vapor pressure is an colligative property, and therefore it depends on the X2. X2 means the number of solute the mole fraction of the solute. That means indirectly it depends on the number of solute particles, and therefore delta P upon P01, which is equal to X2 and which is equal to, what is meant by delta P? Delta P is called as a lowering of vapor pressure, and delta P upon P01 is called as a relative lowering of vapor pressure. It is called as a relative lowering of vapor pressure, and therefore delta P upon P01, which is equal to X2, which is equal to P01 minus P1 upon P01. That means here we have to prove that the lowering of vapor pressure is an colligative property. It depends on the number of moles of a solute. That means it depends on the mole fraction of the solute X2. Then in the last lecture we have completed the relation between molar mass of the solute from the lowering of vapor pressure as delta P. Here we have P01 minus P1 upon P01, which is called as the relative lowering of vapor pressure. That means delta P upon P01, which is equal to W2 M1 divided by M2 W1 divided by M2 W1, and therefore here that means this colligative property, it depends on, that means delta P upon P01, it is relative lowering of vapor pressure, and from that relative lowering of vapor pressure we can calculate the molar mass of the solute, because the molar mass of the solute, because here the molar mass of the solute is denoted by a letter M2, and they are related as delta P upon P01, which is equal to W2 M1 divided by M2 W1. So dear student, that part we have done in our last lecture. So let us start with the second colligative property as a boiling point elevation, or elevation in boiling point. So before going to start the second colligative property, that is the elevation in boiling point, first of all we have to here define what is mean by boiling point. Means a boiling point of a liquid is defined as the temperature at which the vapor pressure of a liquid is becomes equal to an applied pressure. The vapor pressure of a liquid becomes equal to an applied pressure. This is the definition of a boiling point. But for an open container, the applied pressure is equal to the atmospheric pressure, and therefore How we can define the boiling point of any one of the liquid? Because the boiling point is the property of an liquid and it is defined as the vapor pressure of a liquid. It becomes equal to an atmospheric pressure. Means when the vapor pressure of any liquid matches its atmospheric pressure, then at that time that liquid it get boiled. So for the elevation of boiling point, here we have to consider one graph or vapor pressure versus temperature. Here we have to consider one graph of for the elevation in boiling point. Here, dear student, we have to consider one graph of vapor pressure versus temperature. So here we have to draw a graph of a vapor pressure versus temperature. So what is the boiling point? That means the lowering or that elevation in boiling point, they have a direct consequence with the vapor pressure. So from the vapor pressure temperature graph, here we have to predict that how the boiling point it get elevated. Therefore, for that here we have to consider the vapor pressure temperature graph, and this is the pressure here. This is the pressure, it is called as a atmospheric pressure. So this is the line of atmospheric pressure. Why? Because any liquid, when it starts to boiling, when its vapor pressure matches the atmospheric pressure. When the vapor pressure it matches the atmospheric pressure. So here we have a 1 point for a solvent. So consider this is the vapor pressure of a solvent, and when that solvent liquid they have start to boiling, when it is equal to, means when the vapor pressure of that solvent it becomes equal to an atmospheric pressure. So here we have, this is the graph of a solvent, or this is the graph of a vapor pressure of a solvent. When it start to boiling, when the temperature, so this is the temperature at which, this is the temperature, it is called as here so this temperature is called as because this is the temperature of the solvent at which the vapor pressure of the solvent becomes equal to an atmospheric pressure, it is called as a P0B. The vapor pressure, that means here the vapor pressure which is equal to atmospheric pressure and which is equal to 760 mm of Hg, and this is the vapor pressure of a solvent and it is denoted by letter P01 in the lowering of vapor pressure. So this is the solvent, and when it starts to boil, when its vapor pressure becomes equal to an atmospheric, at that temperature it is called as a P0B, and at that temperature that solvent will start to boiling. So the next, as we know, the vapor pressure of a solution is always lower than that of the pure solvent, and therefore the curve for the solvent it is always lies below the vapor pressure of a pure solvent, and therefore suppose this is the point for a solution, and when it starts to boiling, when it vapor pressure it becomes equal to an atmospheric pressure, means when its vapor pressure it becomes equal to an atmospheric pressure. So this is the temperature at which that solution it start to boiling, and therefore the boiling point of a solution is denoted as PB. It is denoted as a PB, and therefore this is the difference in which there is a elevation in boiling point, and therefore this is the pressure, here this is the pressure at which the delta P takes place. Means here the delta P is directly proportional to this difference is called as a delta TB. Delta TB means here the elevation in boiling point, because from this graph of temperature versus vapor pressure, here we have to see that the boiling point of the solution is get elevated, increases when we add the non-volatile non-electrolyte solute to the solvent form a solution. So here from the vapor pressure, as we know that here delta P is directly proportional to delta TB, where the delta TB is called as here the elevation in boiling point. The delta TB is called as a elevation in a boiling point. So here from this graph, here we have a clear that the vapor pressure, they are having a direct consequence with the boiling point. So here therefore the boiling point of the solvent is elevated by dissolving a non-volatile non-electrolyte solute into it, and therefore a solution containing a non-volatile non-electrolyte solute boils at a temperature higher than that of the pure solvent, and therefore the boiling point of a pure solvent is denoted by a letter here. The boiling point of a pure solvent is denoted by a letter T not B, and the boiling point of a solution is denoted by a letter TB, and therefore here the elevation in boiling point, that means delta TB, which is equal to here the boiling point of the solution is higher than that of the pure solvent, and therefore here we have to TB minus T not B. That way this is called as a elevation in boiling point. TB, that means the boiling point of a solution, and T not B is the boiling point of a pure solvent. So when we add a non-volatile non-electrolyte solute to the solvent, then the boiling point of a solution is get elevated, increases. Therefore that increased is denoted by this letter delta TB, which is equal to TB minus T not B here. From the thermodynamic consideration here and the experiments for a very dilute solution, it is observed that this delta TB is directly proportional to the small m. Small m is called as a molality of the solution. This is called as a molality of the solution. From the thermodynamic consideration and the experiments for a very dilute solution, and here we consider a binary solution as a dilute solution, and therefore from the thermodynamic consideration here we can say that delta TB is directly proportional to m. M means the molality of the solution, and if you remove the proportionality sign, then here delta TB, which is equal to KB into m, where KB is called as a proportionality constant. If we remove the proportionality sign from this, then here KB is called as a constant, but it is called as a proportionality constant, and it is in the expression of the elevation in boiling point. So this KB is called as here, this KB is called as a boiling point elevation constant, boiling point elevation constant, or these Kb is also called as ebuloscopic constant. Ebuloscopic constant. These Kb is called as a boiling point elevation constant because it is in the expression of the elevation in boiling point. This Kb is called as a boiling point elevation constant or a ebuloscopic constant or the molar elevation constant. This Kb is called as a boiling point constant or the molar elevation constant or the ebuloscopic constant, and this ebuloscopic constant is defined as, that means here the Kb which is equal to delta Tb, that means elevation in boiling point divided by m, and if in this expression if m is equal to 1, then Kb which is equal to delta Tb. Then here for m is equal to 1, here the Kb which is equal to delta Tb, and therefore this Kb, that means the molar elevation constant or the ebuloscopic constant is defined as, here it is defined as the elevation in boiling point, produced by 1 molar solution. The elevation in boiling point, that means delta Tb, produced the elevation in boiling point produced for a 1 molar solution. Therefore, the ebuloscopic constant is the boiling point elevation produced by 1 molar solution. So, what is the unit for these Kb? And for the unit here, we have Kb which is equal to, here we have Kb which is equal to delta Tb upon 1. Here Kb which is equal to delta Tb upon m. Delta Tb means the elevation in boiling point, and they are having a unit Kelvin. And what is the unit for the m? M means molality. Therefore, they are having a unit mole per kilogram. And therefore, they are having unit Kelvin per kilogram, means Kelvin kilogram per mole. What is the unit of a Kb? The unit of a Kb is Kelvin kilogram per mole. So this is a very important part for the exam point of view. What is the unit for a Kb? Kb having unit Kelvin kilogram per mole. So this is all about the elevation in the boiling point, that means delta Tb. Means when we added a non-volatile, non-electrolyte solute to the solvent, then there is an elevation in boiling point of the solution takes place. So dear student, this is the definition and expression for the elevation in boiling point. So next part, that is here how we can calculate the molar mass of the solute from the boiling point elevation. How we can calculate the molar mass of the solute from the boiling point elevation. Because the main use of all these colligative property or main application of all these colligative property are from this qualitative property, we have to calculate the molar mass of the solute. We have to calculate the molar mass of the solute. So we have to start this with, as we know here, delta TB, which is equal to KB into M. We started with this, that means from the thermodynamic consideration for the very dilute solution, the elevation in boiling point is directly proportional to the molality and is equal to Kb into M. But what is mean by molality? And hence here we have M means a molality, and therefore M means molality, which is equal to N2, number of moles of solute present in 1 kilogram mass of the solvent. That means W1, which is always in a kilogram. W1, which is always in a kilogram. And therefore here M, and therefore M, which is equal to, what is the value of N2? N2, which is equal to W2 upon M2. As we know, N2 means the number of moles of solute, which is equal to W2 upon M2. So M, which is equal to here W2 upon M2 divided by W1 in kilogram. But when we calculate the number of moles of either solute or solvent, then the weight and the molar mass of the solute, which are in a unit of gram. So all these two units, they are having a gram and weight in a kilogram. So here therefore delta TB, which is equal to KB into M, means W2 upon M2, W2 upon M2 divided by W1. And therefore here delta TB, which is equal to KB. Here if we simplify this, then we get KB W2 upon M2 W1. KB W2 delta TB W1. So here we have this is the relation between the molar mass of the solute and elevation in boiling point. But when we have to convert this in a gram, so we have to multiply. We have to multiply this with the 1000, and therefore delta TB, which is equal to, because we have to convert it into a gram. All these two, number of moles means weight and mass, they are present in a gram. Therefore when we convert the kilogram into gram, then we have to multiply this equation into 1000. Therefore delta TB, which is equal to KB, here delta TB, which is equal to, we have a KB 1000 W1, here we have a M2 W1. So here we have a W2, not a W2. Here we have a W2. Therefore delta TB, which is equal to KB 1000 W2 divided by M2 W1, and therefore for the calculation of the molar mass of the solute M2, if we have to rearrange this, then we get here KB 1000 W1 divided by delta TB W2, here we have a W1. So from this expression we have to calculate the molar mass of the solute M2. So M2, which is equal to here M2, which is equal to KB 1000 KB W2 divided by delta TB W1. Delta TB W1. So dear student, in today's lecture we have completed our second colligative property as elevation in boiling point, and here we have an expression as the elevation in boiling point delta TB. That means here we have considered here delta TB, which is equal to KB into M, and it is related with the molar mass as M2, which is equal to 1000 kb W2 divided by delta TB W1. So these two formula, they are very important for the boiling point elevation, where Kb is called as a ebullioscopic constant. So dear student, we will stop here. We will meet in the next lecture. Thank you.